energy that an object has while it is in motion. If an object is moving, it has kinetic energy. There are many instances of kinetic energy on a cruise ship. One of these instances is the rock climbing wall on the main deck. When a person goes rock climbing, they get to the top of the wall and then they go back down. When they move back down, they have kinetic energy because they are in motion. We set the speed of this kinetic energy equal to 0.5 meters per second because we decided that it would take about 15 seconds to get to the bottom of the grounds, and the wall is 7.5 meters high. We then use the equation kinetic energy is equal to 1/2 times the mass of the person times velocity squared. The mass of the person is approximately 75 kilograms because this is the average mass of a man. After we do the calculations, we see that kinetic energy is equal to 9.4 joules. Okay, next, conservation of energy is the concept that energy is neither created nor destroyed. So energy is just transferred between different forms. So it can be transferred from radiant energy to potential energy to kinetic energy. So an example of conservation of energy on the cruise ship is on the knee-loom deck of the water slide. So when the person is at the top of the water slide, they have gravitational potential energy, because if the objects were removed, they would fall to the main deck. When they are moving down the slide, they have kinetic energy because they are in motion. And then once they get to the pool, if they're at the bottom of the pool, they have gravitational potential energy, because if this deck were removed, they would fall back to the ZRL, or the main deck. So the calculation we used is the initial energy is equal to the final energy. And so the initial energy at the top is the gravitational potential energy, which is mgh, is equal to the mgh of when they're at the bottom of the pool, plus the kinetic energy that they have when they are moving on the slide. After we do all the calculations, we see that the velocity that they're moving on the slide is 10 meters per second, and the energy that they have overall is conserved.
Gravitational potential energy is an energy an object has due to its position in a gravitational field. So we can find this on a cruise ship when the person is playing shuffleboard on the Lido deck. So if the person is standing up there, then he has gravitational potential energy, because if the floor wasn't there, he would fall down and be pulled by gravity. So to calculate gravitational potential energy, use the formula UG equals mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. So for height, I set the Machuca deck level as the ZRLs. The Machuca deck is 4.5 meters below the main deck, and the Lido deck is 8.0 meters above the main deck. So the height would be 8.0 plus 4.5. The mass would be 75 kilograms, which is around the average mass of a person, and the G would be 9.8. So calculating that would get 9,187.5 joules, and with sig figs that would be 9,200 joules. Next is simple harmonic motion. So simple harmonic motion is repetitive motion around a single point. So this can be found on the diving board at the Devon deck. So when a person steps on the diving board, the springs are compressed, and when they jump off, the springs are released, and then the board will bounce up, back and down, back and forth around the equilibrium position, which would be its level resting position. And if you wanted to calculate it, you could use F equals negative kx, where F is the restoring force, which is proportional to displacement, k is the spring constant, and x is the distance away from the equilibrium position. Finally, there's refraction on the cruise ship. So refraction is when waves either speed up or slow down when they enter a new material. So this can be found during the treasure hunt on the Machuca decks with the cell phone. The cell phone emits an RF wave that hits a glass door, and so the cell phone it comes from air, which has an index of refraction of 1, and the glass has an index of refraction of 1.490. Since the glass has a higher index of refraction, the waves slow down when they enter it. And to calculate that, you could use Snell's law, which would be n1 sine theta 1 equals n2 sine theta 2. So then we can plug in, the cell phone wave comes at 29 degrees to the normal, so we could use 1.0 times sine 29 degrees equals 1.490 times sine theta 2. And then calculating that would get theta 2 to be 18.9883, and with sig figs it would be 19 degrees.
So elastic potential energy is when potential energy is stored as a result of stretching or shrinking the spring, and it's equal to the work done to stretch or shrink the spring. And this can be seen on the rock climbing wall on the main deck. And this is the zero reference level. So when the spring, which is the bungee cord, is stretched 4 meters, it causes elastic potential energy. And then we calculated this using Hooke's law first, and Hooke's law is F equals negative kx. So we knew what the force was, and we knew what x was, and x is the distance away from the 0 reference level. And so we just had to solve to find k, and we found k to be 16.25. And then we plugged that in back into the equation for elastic potential energy, and with sig figs it would be 512 joules. And then mechanical waves are any waves that require a medium to move through. An example of this would be ripples caused by a kid jumping into the pool on the Devon deck. And these ripples are examples of mechanical waves. And this is what wave would look like. And then we solve for the energy in a mechanical wave because we know that E is proportional to the amplitude squared. And we found that an average kid would weigh about 40 kilograms, and that would cause an amplitude of about 0.125. And then we just had to square that to find what the energy was, and we found that was approximately 0.0156 joules. And diffraction is when a wave bends around an object and disperses its energy. This can be seen in the tanning booth, and if there's a person tanning, the waves hit the person, but as soon as there's an obstruction, it has to bend and disperse its energy in the space in between. And this is a more zoomed in version of that.
So radiant energy is energy associated with electromagnetic radiation. Example of these are radio waves and TV waves. On the boat, we have the pool on the Neelam deck, and the heater in the pool is an example of this, because it's infrared, so we know that the wavelength of it is 750 nanometers. So to calculate the energy, we know that E is equal to H times F. So H is Planck's constant, and F is the speed of light over the wavelength, which we now know. So all this calculated is 2.7 times 10 to the negative 19 joules. So electromagnetic waves are waves which do not require a medium to go through. So we have an example on the Machuca deck when they're playing the treasure hunt game. The lights in the room are an example of this. So that's because they are visible light waves, and the energy is carried through packets called photons. So interference is when waves meet in a medium. Waves pass through each other and continue unchanged. Destructive interference is when the resulting wave's amplitude is less than the original waves. Constructive interference is when the resulting wave's amplitude is greater than the original wave. So an example of this we have is jumping into the pool on the Devon deck. There are people already in the pool there's people already in the pool, which cause previous waves, and when jumping in the pool, you create new waves, and these two combine an entire new wave. So work transfers energy, and if there's change in energy, work has been done. In order to do work, a force must be applied, and the object must change position in line with the force. So an example we have is the shuffleboard game, and it's W is equal to change in energy, or W is equal to Fd. So we set F, which is the force, as 5, and D is the distance, which is 2 meters, and this makes equal 10 joules.